This lecture is mainly about sketching graphs and their transformations. We'll be dealing with some very simple cases where we're just moving around a graph in a two-dimensional Cartesian coordinate axis. But we could indeed make a transformation between, say, a rectangular coordinate system and a spherical or cylindrical or ellipsoidal coordinate system. And also, we apply transformations to change the representation of a particular type of data. Image data is a very good example of this. You can see in the picture some sonar imagery. Sonar imagery is created from the intensities of returning acoustic signals when they bounce back from the seabed. They create what are called textures, and you can see 5 different textures in this picture. As human beings, our visual system can easily discriminate between these different types of texture. We just know that there's something different about them. But if we wanted to give this information to a machine, such as a computer, and get it to automatically distinguish between these different types of texture, then we'd have to transform the data in some way. One way of doing this is to apply what's called a filter bank to the image data. And a filter bank is made up of many individual filters. Gabor filters are used quite often in this type of process because of their similarities to the human visual system in the way that the visual information is processed. By applying the filter bank to the image data, we generate what's called a feature space. And a feature space contains many feature vectors or patterns. A pattern is just a string of numerical values that represents a small region of the image. Once we've created these patterns, the computer can then distinguish between them, provided we set up some learning process. We can train a machine to learn to recognize the different types of numerical pattern corresponding to the regions of the imagery. It's called pattern recognition, and it's synonymous with machine learning. So we can take a sonar image, we can get a computer to process that image and output a map showing different regions of texture, and those textures correspond to different regions of the seabed. Of course, we can only do this by computer, but we need to understand the basic mathematics of the transformation in order to write the computer code that performs this process. But having said that, the complexity of the system required to carry out this type of process is much greater than the basic mathematics that's used to apply the transformation. Okay, let's get back to the theme of our lecture, and we'll start by considering some sketches of cubic graphs. You should be able to sketch the graph of a cubic function when it's expressed in factorized form. We'll look at 3 different cases of this. In the first case, the function is expressed as x minus a all cubed, and it has what's known as a triple root. In the second case, the function is expressed as a product of what's known as an irreducible quadratic factor and a linear factor. In the third case, we'll consider the function when it's expressed as a product of 3 linear factors. Let's have a look at the animations now. In the first animation, we'll look at the graph of the cubic function f of x is equal to x minus a all cubed. To begin with, I've set a equal to 0, so in fact this graph is showing f of x equals x cubed. The important points to note about the graph of x cubed is it has a triple root at x equals 0. You can also see that as x heads off to positive infinity, f of x will also head off to positive infinity, and likewise, as x goes to negative infinity, f of x will head off down to negative infinity. You can also see that the shape of the graph is quite flat in the interval between about minus 0.5 and 0.5. If we change the value of a, we can see what effect that has. In the case where we have f of x is equal to x minus 1 all cubed, you can now see the triple root occurs at x equals 1. There's no change in the shape of the graph. Going in the other direction, we have f of x is equal to x minus 3, which is going to be x plus 3 all cubed, and the triple root will occur at negative 3. Now we'll have a look at the second case. In the second case, we'll consider the cubic function expressed as a product of an irreducible quadratic factor and a linear factor. An irreducible quadratic factor is a term that cannot be expressed as a product of linear factors in the real number system. We can express it as a product of two linear factors with complex numbers, but we'll be looking at that a little bit later in the pre-calculus course. So we have g of x is equal to x squared plus 20 multiplied by x minus 4. And obviously the x squared plus 20 is our irreducible quadratic factor. Let's have a look at what happens when we change the value of the number inside of the irreducible quadratic factor. Now this is where things start to become interesting, because you can see that the curve is starting to bulge upwards on the left. So at x squared plus 3, we've got a distinct hump appearing. And this hump becomes more pronounced as we go to x squared plus 1. So with the irreducible quadratic factor, there would only ever be one point at where the curve cuts the x-axis, corresponding to the linear factor here. So in this case, the crossing point on the x-axis is going to be at x equals 4, and that will remain fixed whatever we do to this irreducible quadratic factor. You can see that the curve is always going to cut through the x-axis at x equals 4. The y-intercept is changing, and you should be able to see that the y-intercept is going to be a product of the value in the irreducible quadratic and the linear factor. So here we've got 5 times negative 4, which gives us a y-intercept of minus 20. So this irreducible quadratic is actually controlling how much this curve bends, and eventually it'll bend enough to create this, this hump in the curve. Let's have a look at the third case then, when we express the cubic as a product of 3 linear factors. So you can see with 3 linear factors, we have 3 distinct roots. The first one is at x equals negative 5. And you can see in the brackets there it says x minus 5, which is the same as x plus 5. The second root is at x equals negative 1, corresponding to the factor x plus 1, and the third root is at x equals 2, corresponding to the linear factor x minus 2. The y-intercept is at minus 10, as we would expect. It'll be 5 times 1 times minus 2, which is minus 10. What we'll do then is we'll see what happens to the shape of this graph when we just change the first linear factor here. So the x plus 1 and the x minus 2 will remain fixed, and we'll just change the first linear factor. So we should be able to predict then that obviously the roots x equals negative 1 and x equals 2, they're not going to change. It's only this root here which is going to change. So let's have a look and see what happens. So as we move along like that, we can now see the root has moved to minus 3. Then if we move it to minus 1, we've now got a double root at x equals -1. Then if we move it along a little bit further to 0, you can see the root is at the origin there. And then on to 2, and we get a double root at x equals 2. And then finally we'll move it all the way along to 5 there. So you can see that the shape of the curve, it'll become flatter in places. Around here you can see it's flatter around the x-axis, but here the hump or the curvature is more pronounced, as it was over here. So this alters the shape of the graph, the amount by which it curves, and it alters obviously the position of the root, but the other roots at x equals -1 and x equals +2, they never change. We'll have a look at sketching a graph for ourselves now. Hopefully then, after watching the animations, you should have a good idea of the shape and the basic properties of the cubic curve in 3 different cases. So what we're going to do now is just have a look at an example where we have to figure out how to construct a sketch for ourselves rather than allowing a computer to do it for us. And we've got the function f of x is equal to -x multiplied by x minus 1 and 2x plus 1. The first thing to note about this, which is going to be a little bit different to the animations that we looked at just now, is that our coefficient of x cubed is going to be negative. But we should easily be able to figure out what's going to happen with that, because we saw in the animations that with the positive coefficient of x cubed, the curve went off down towards the bottom left and up towards the top right. So with a negative coefficient of x cubed, that situation is going to be reversed. So we're going to be coming down from the top left and heading off to the bottom right. Alright, so what else do we need to do? Well, we can write down the roots straight away, can't we? That's very easy to do. We can see that our 3 roots are going to be at x equals 0, x equals 1, and x equals -1/2. So let's just mark those on there. We've got x is 0, x is equal to 1, and x is equal to -1/2. As we said before, the graph is going to come down from up here in the top left. So it's going to go something like this. And we know it's going to go down towards the bottom right, so it'll head off down here somewhere. Well, knowing that, there's really not many other places it can go to now. In fact, there's only one way we can finish off this graph. So it has to go down like this and then curve back up. It'll reach a maximum around here somewhere and then curve back down. So that's it. Now have a go at the multiple choice question.